Hello and welcome everyone. Today we have another Envision Tech Talks webinar. Our topics today is optics and lenses. We have 3 presentations. What we're still waiting for some minutes until everyone arrives. As you see, we have presentations from COVA, Edmund Optics, and Opto Engineering. And as we have some time, I will skip a little bit. Next week there will be another webinar. Then our topic will be machine vision cameras. As you see, Bauma, IO Industries, and Matrix Vision. In 2 weeks, there will be our last webinar before the summer break. Then it's deep learning. After the summer break, we're starting with the Envision Tech Talk solutions. It's more about solutions and systems, not so many components. And as you may know, we have also Envision Products newsletter, which will be sent out every 2 weeks. If you like to become a subscriber, just go to our website. But today, our topic will be, of course, optics and lenses. If you have any questions during the webinar, please use the Q&A session. Your questions will be answered after each presentation, and then there will be a final Q&A session after the last presentation. So I think we're starting looking at the watch. It's 2 o'clock. So once again, my name is Peter Ebert. I'm editor-in-chief of Envision Magazine. I'm also the host of this webinar today, as always. And our first presentation comes from COVA. So Daniel, the stage will be yours. I just close my presentation so you can start with yours.
Okay, I start to share my presentation.
Yeah, now it's starting.
Can you see it?
I see it, but I also see the next pages. Yes, now it's perfect.
You see the next?
Yes, now it's perfect. Daniel, stage is yours.
Thank you. Yes, hello everybody, and thank you for joining. My name is Daniel van der Zand. I'm sales manager here at COVA for machine vision lenses. Today I will talk about mechanical design and transmission as criteria for lens selection. So I will pick out certain features of mechanical design and transmission and explain them basing on examples of some of our latest developments. So if you here look at this slide on the right side, you see the criteria you would usually look first at when choosing lenses. So these are like something like sensor size of lens, pixel size, or focal length. These factors, we are not looking at these factors today, but we are looking what you see on the left side. Sometimes mechanical design and transmission become crucial criteria for choosing lenses. That is why I will explain some characteristic of mechanical design, such as ruggedization, size, floating mechanism, and I will briefly touch on several characteristics of transmission. Before I do that, I will briefly introduce COVA as a company. As some of you might know, COVA is a Japanese company. It was already founded at the end of the 19th century, at that time as a trading company. Since then, the company has prospered into a multinational company with 6,500 employees, with a lot of different business areas. So you see here offices around the globe. And business areas, still trading is a big part of the company. For manufacturing, COVA has a big part of manufacturing medical products. And one other important part is production of optical products, the part I represent. COVA started to produce optical products already in the 1940s. And from the beginning, it was lenses and other optical products such as spotting scopes or binoculars. Regarding lenses, we focus on solely B2B lenses, lenses for industry use. For this, we have two business areas. One, machine vision lenses, which are mostly fixed focal lenses, C-mount, and also security lenses, which are mostly motorized zoom. And for security, we also have a low light camera. For both areas, we also offer customized solutions. In Düsseldorf, Germany, here is our sales hub for Germany. Here we have a big warehouse with most items on stock and our technical service department. So what makes COVA as a lens manufacturer different? We have a very wide product range. In our catalog, you will probably find, for most applications, you will find a standard lens. We position ourselves in the higher optical quality segment and try to differentiate ourselves by innovative new developments. So we try to differentiate ourselves by technical features and not by price. And beside this, we offer customized solution in a quite flexible way. Now I will start the topic, mechanical design. So ruggedization. COVA has developed a so-called ruggedized lens, which due to its design makes the lenses shock and vibration resistant. I will explain how this design is different from standard lenses. So if you look here on the image on the upper left, you see this lens has this red locking ring for focusing. So instead of standard screws, you have a locking ring. And if you look at the left side of the picture, you see you can take off the front part of the image of the lens. And here you can put in the interchangeable iris plates you see in the picture below. So here in this next slide, this becomes clearer how these lenses are handled. And if you also look on the right side, you see how these lenses compare to standard lenses. On the upper right side, you see the iris of a standard lens. It's iris plates which you move and close and open with some sort of mechanical mechanism. The disadvantage of this is that in shock and vibration, this could cause dust due to the friction of the iris plates, and overall it's much less stable than this construction you see here on the left side with the fixed aperture. On the lower right side, you also see the standard lenses with screws. Obviously, these screws could fall off under shock and vibration. And the most important part for the ruggedized anti-shock and vibration lenses is the inner lens elements are all glued together. The glass elements are glued, which makes the optical axis very stable. And this is an important factor for applications such as 3D measurement, for which you need a really stable optical axis so that you can calibrate the system. Of course, we measured this, the pixel shift from object side to sensor side after inflicting the lenses to a certain shock and vibration standardized test. And there is a minimal pixel shift with these ruggedized lenses. Just, I want to point you out this illustration you see here on the lower right. This blue circle is a 1 micrometer circle. And for this specific lens we show here as an example, there is a minimal pixel shift measured. As I said, the advantages, no screws are falling off. This I didn't say that there can be no tampering, not even by mistake. Somebody will change the setting of the lens. No dust from friction of the iris plate, and the stable optical axis I mentioned. And this makes these lenses exciting solutions for any robotics application, for fast-moving conveyor belts, for forklifts with mounted vision systems, and as I explained, for a 3D measurement system for which the stable optical axis is a crucial factor. Now I will move into the next aspect of mechanical construction, which is size. Oh, sorry, I forgot one thing. I want to mention also these standard lenses for the ruggedized construction we just explained. We have two standard lens series, which is 1 inch 5 megapixel lens series and a 2/3 inch 2 megapixel lens series, both with a very wide range of focal lengths. And with these, you can cover quite a lot of application. And so you have this ruggedized anti-shock and vibration option for these many sensors which are mentioned here. Now, as I said, I want to move into size. We try to make the lenses, of course, as small as possible, but the limiting factor is the higher the optical quality or the higher the resolution, the more glass you need to use. And here I want to present you the example of one lens where we could find a trade-off to make this lens very, very small. So this lens has a relatively high resolution, 2/3 inch for sensors with pixel size about 3.45 micrometer. And by making certain trade-offs in iris, f-stop, and in making trade-offs in resolution for distances further away, we could develop this very small, tiny lens, which only has a diameter of 3.2 centimeters and a maximum length of 2.7 centimeters. As I said, not in all applications this is relevant, but in some applications, as you see here, you have limited space. On the pictures, you have limited space and you have small housings. So then these compact mini lenses come into play. And by being that small, these lenses also have one other positive side effect. They also have a more stable optical axis. So they can be used for robotics, also for any application where there is a shock and vibration. Of course, these lenses don't have the ruggedized design I just explained. So we could say they are semi-ruggedized. But one feature as a side effect of being that small is that they have the stable optical axis and a reduced focus shift from object side to sensor size, which also, of course, with these lenses, be verified in standardized tests. Now I want to move on to the next topic. So based on this specific lens series, I want to explain two other aspects of lenses. So this is a 24 megapixel 1.1 inch lens series, which has a quite high resolution for sensors of pixel size down to 2.5 micrometer, so covering most of the Sony sensors of the latest generation you see listed on this side, also with a wide range of focal length starting from wide angle 6.5 millimeter. And based on these lenses, I want to explain first one mechanical feature, the so-called floating mechanism. Floating mechanism is a mechanism to improve the performance of lenses from a close distance to distance further away. And how is this done? So if you look at this illustration here, and you see this lens in the middle, it's a lens before being focused. If you look at the illustration left above, you see a standard lens after being focused, and you see the lens elements stayed in the same distance to each other. And if you look at in the illustration on the left below, where it's written lens with floating, you see the lenses after being focused, the lens elements have changed its distance to each other. And how is this achieved? If you look here on the right side, you see a lens without housing. And due to this specific mechanical construction of this cam threads, you see how the distance of the lens elements are changed to each other. And as I said, the effect is improved performance from far away, from close to far away. All of our higher quality lenses have this mechanism. And now one other aspect, this is the aspect of transmission I will talk about. all our high quality aspects also have what we call the broadband coating. If you look here at the thick red line, this is a broadband coating, which increased transmission up to near infrared, up to about 900 nanometer. The other more standard lenses have what we see here, the blue line, the so-called peak coating, where the peak is at about 400 nanometer, and then the lens drops to 60% in transmission in near infrared. And these two coatings are the most used coating for all of the lenses with use in visible and near. And now I want to expand this topic of transmission, and I want to introduce one other new lens series, which has a quite different coating and different transmission than any standard lenses we had before. And this is our so-called VisSur lens series, which has a increased transmission from what you see here on this illustration, 450 nanometer up to 2000 nanometer. And one additional aspect here is that in this wide range of transmission, also there is a decreased focus shift. Usually, if you would change the lighting, you would have to refocus the image because it goes out of focus in different wavelengths. But due to the optical design of these lenses, this natural focus shift is decreased here. So this is the lens series for 1 inch, which fits very well to some Sony sensors, which IMX 990, 991, which came out last year. It also very new about this lens, that this is the lens with transmission up to shortwave infrared, which has a relatively high resolution for sensors with pixel size 3.1 micrometer. And what does this do? So here you see the sort of application this lens can be used for. Here on the upper left side, you see the famous images of the apples. So at visible, the apple, yeah, you couldn't see rotten part or pressure points at apples at visible, which can be seen at shortwave infrared. You see here on the right. Other applications would be what you see on the upper right side, looking through packaging, or there are certain materials in sorting which seem different only in SWIR, but not invisible. And this lens plays out its advantages most when you use it with a VisSur camera and you switch with different lightings. So then you can use one system and cover it all and switch back between visible and shortwave infrared. So that was about the technical aspects. In the end, I would just to point out to you on our website, you can find all optical data of the lenses. You can find videos. You can download 3D data. We have a newly updated lens calculator with which you can calculate the lens for your use. And yeah, this were some aspects which I highlighted, which you usually don't think first about, but which probably you think last, or which are only important in certain very specific use cases. So I tried to give you an overview of what aspects can be important for these topics based on the examples of some of our latest developments. And if you have any questions, please feel free to contact me. Here are my contact details, and I'm looking forward to the questions you have now.
So thank you, Daniel. And now it's the time for your questions. Please use, if possible, the Q&A session. The first question is, are you supplying lenses to infrared camera manufacturers?
Yes, of course. Yeah, so infrared, as I said, we have these lenses optimized for infrared, shortwave infrared. So yes, we do, yeah.
Mm-hmm. And you mentioned your ruggedized lenses. What volume do you need for ruggedization of standard lenses?
Well, it depends. So if you say ruggedization, if you just want to glue the inside lens elements and keep the screws and the standard iris, then it can be done from 50 pieces, if that is easy to do. For some more complicated lenses, it's quite difficult to do that, so it cannot be done at all. But if you want to have the whole ruggedized design with also the mechanics and the locking ring and iris plate, then we can say probably 200 to 300 pieces at least. Mm-hmm. So it depends.
You mentioned NER and SWIR lenses. So that's a question about middle wave ER and long wave ER lenses from Kowa. Do you have any?
No, we don't.
And what about half-sol SWIR lenses? Any plans for it?
Say again?
What about ein halbe Zoll, half?
Half inch. Okay.
Half inch.
Well,
sorry,
I mean
inch. Sorry. Yes, of course. What about half-inch SWIR lenses? Yeah. Any plans for it?
Well, with this 1-inch SWIR lenses we have, you can of course cover the half-inch sensor, so you can use the existing half-inch lenses. But at the moment, there are no plans to make it specifically for small sensor sizes.
Mm-hmm. And can the ring screw to adjust the focus aperture be locked?
Yes, you screw them and you lock them, and we also recommend to put some drops of glue so that you glue them. Mm-hmm. Additionally.
And do you supply also IR SWIR filters?
Well, usually we don't supply filters, but for this new series, I just recommend. I just introduced this with SWIR. We supply some filters from MidOpt. You can go to our website and check it out. We selected some specific filters which fit this new VSWIR series very well, and we can supply them together. Yes. Hello?
It almost seems like we lost Peter.
Oh.
Let's give him a minute. Let's see, maybe he comes back.
Yeah.
If not, we can also just go on. I mean.
Yeah, so I think now 20 minutes are up.
Yeah.
I don't know why. Yeah, if the next person starts.
Yeah. Yeah, we agreed on the order before this went live. So I already know that I'm supposed to do the presentation now. So let's just hope that Peter will come back at some point in time. Anyway, for the time being, hello everyone. I'll introduce myself since Peter's not here. My name is Boris Lange. I'm with Advent Optics. Give me just 1 second to share my screen. So I got the second presentation of today's webinar. And I have a couple of slides here that are very, very similar to what Daniel just showed us. I will move over these very quickly. I only have to add 1 or 2 things. I think everything else was very well explained already. And then I will focus my talk on a little bit more on the temperature side, and the remaining time we can use for some questions, either immediately after the presentation or at the very end, where we have the big group discussion with where all of the presenters can comment on your questions. So that being said, I'll just start. It doesn't seem like Peter is back, or even if, I'm not sure. I'll just keep going here. So yeah, harsh environments. We already heard from Daniel how active COVA is in that field, and it's not a different story here at Edmund. We see the same market, we serve the same market in harsh environments. Has been a trend for many, many years that also impacted, of course, our product portfolio over here. When I started, it came up every now and then. So like 6 years ago when I started at Edmund, but in today's time, there's not a single project to develop a custom lens without any discussion about either shock and vibration, or temperature, or humidity, or stray light. And that's essentially also my agenda for today for the next 15 minutes. As Daniel already explained everything very well, as I said, on the shock and vibration part, I will be very quick on those slides. And then we have some more time to discuss everything related to temperature. Humidity, I put it here, and stray light, I put those two topics here for the sake of completeness. Because they also gain traction in the same manner as the first two topics here. I didn't prepare any slides on those. Humidity is fairly straightforward anyway. Most people already know the existing solution here. You put a tube, a protection tube on your camera. We also now launched a new product series that already is sealed with O-rings that you can use directly in humid environments. But as I said, that's just mentioned for completeness, and stray light is its own science and topic in itself. Happy to discuss any of your questions later on. For the time being, I'd say let's just get started with shock, vibration, and temperature changes. And within shock and vibration, as I said, you've seen this already also from Daniel's slides. If you look at such a nice lens in the inside, the optomechanical design is what decides about its use case in the harsh environments. Iris leaves, focus mechanism, including the floating element design, spring detents, there's lots of things that can break. So the first step, it's quite logical to just remove that. That's a little bit of a difference, that's why I'm bringing it up. Because this is now what we call industrial ruggedization here at Edmund. You can just remove the fixed aperture, you can remove the helicoil focus, so that you essentially just end up with a big M12 lens in terms of the handling and feeling. And like Daniel's mentioned, they're more robust, they're even more compact, so smaller size. They also have less weight, which again, quite important actually for robotic applications in particular. And the other thing that I might have missed is that usually you also save cost. So it's a real good package and a really good idea to use this kind of lens. The only drawback is that you have to deal with the fixed F number. You've seen it with the COVA lenses, you can swap them in and out. You can't do that with our lenses here. But yeah, the general attitude is anyway that people would start to design their system with the normal lens with an iris. And then as the project proceeds, you can set up your illumination, your exposure time, your gain, and everything around the system level. Make sure you get a nice image, and by that time you define your F number, and then you can move over to a fixed aperture version. This slide I'll just immediately skip, because this is now then exactly what Daniel also showed. Maybe the only difference that Edmund has this mount over here that is very similar to the Schneider mount you might be familiar with, where you can also just lock the entire thing in place, and the clamping force attacks along the entire circumference of the imaging lens. But yeah, this was already more or less discussed, especially for 3D system. It's really important, or yeah, any calibrated system, also laser triangulation sensors. If you just want to use such a thing on a robot, then yeah, you want to have an easy life, of course. You just want to mount it on the robot and rely on it. But in order to do so, the developer of that instrument has to worry a lot about the correct choice of optics in there. So very challenging environment and very nice topic. Yeah. One more thing, you've also seen these pictures from Daniel before. I just want to point out one more thing. It's really important that you get down below that 1 micrometer pixel, 1 micrometer range with your ruggedized product. It's much smaller than a typical pixel size that is used today, but because of all the advanced algorithms and the subpixel interpolation, it's really critical. I see very often specs like 1/10 of a pixel size is what you have to guarantee that your beam pointing is on spot and that your image doesn't move across the sensor of your camera, which makes perfect sense if you think about the stereo camera system with 2 cameras left and right of each other. And if you want to really strive for precise results with those instruments, you really need that beam pointing specification to be on spot and much, much smaller than just 1 pixel size of your sensor. That wraps up the entire ruggedization thing and mechanical shock and vibe chapter already. So the remaining time we can use to discuss temperature. And when it comes to temperatures, you can actually see a lot of things if you open data sheets from lenses. Might be actually that you don't see any specific temperature spec at all in a data sheet. Sometimes there's only a storage temperature called out. And then there's also, of course, some that call out the operating temperature range. However, it should really be noted that even with it's a range of temperatures, but you should stay at a constant temperature within that range. If your operating temperature range to the data sheet is like -10 to 60 degrees, then it does not mean in any case that you can just mess around with the temperature as you want. There's no way that you will see it defocus over such a big range in any case. So, but as long as the temperature is within that range, the lens will, and is constant, the lens will of course stay in focus, and also the lens is not going to break if you operate it in the designed range. So that's that. However, what ultimately matters for a lot of applications, especially if you think about agriculture or all things autonomous, drones, things that go outside of the factory floor, outside into the real world. But even within factory automation, there's more demanding, higher end applications that really strive for a level of precision where you cannot longer ignore the impact of temperature on the optical system or on the machine vision system in its total. And exactly here where it gets interesting, of course, it also gets very complicated. And at least I haven't really seen a good a quantitative measure of how image quality, be it a defocus, a focus shift in millimeters, or an entire MTF curve. I've never seen such a thing in a data sheet. Also Edmund doesn't provide anything like that. There's simply no simple answer of how do your optics change, how does your imaging performance change with temperature. And so I would want to shed some light into why that is, and I want to create a little bit of an understanding of what's going on in the lens and what do you have to think about and consider when you're designing such a system. So let's have a look at this picture again. Same lens as before, some photography lens, but the fundamental principles apply to machine vision lenses in the very same way. So if you look at the optical design by itself, ignore all the metal, just look at the glass or plastic if you have it. Then if you change temperature, your element shape is going to change. The thickness is going to change, the radii is going to change a little bit, the ratio is going to change, and by that, the focal length essentially of each and every single optical element in your imaging lens is going to change, and it will all add up. And if it's not controlled, it will add up arbitrarily. And so you have to expect some kind of a defocus within any range, whether that's within an operating temperature range, or also outside of it. Doesn't matter if it's 50 degrees or 10 degrees or 1 degree. Physics is physics. Things move, things grow, things shrink. And so you have to expect that to some level. Then also, of course, the lens distances, because not only the optics, but also the metal will react to the temperature. So also the distances between the lenses can increase or decrease depending on the exact mechanical layout of the lens. And very fundamentally, also, of course, the index of refraction of every single material, of every single optical glass used in your design is going to react differently with changing temperatures. And if you take another look at this beautiful layout here, you can see these lenses are really nicely seated in their mechanical seats. But as temperature increases, those seats will increase their size. So the optics are a little bit looser all of a sudden in their seat, which as soon as it comes to shock and vibration, that's already quite critical. But also the other way around, if you decrease temperature, it's quite critical. If your bore gaps are very small and your temperature gets low, then there's an increased pressure on your optical components, and it is not unheard of that this pressure goes to a level where your optic, your single element inside your lens just breaks and is damaged completely. So that's definitely can happen. It can even be a little bit worse. Some glasses really react very sensitive also to temperature gradients, meaning that if you change the temperature rapidly, so now we include the temporal effect of the temperature change as well. Some glasses really don't like that and just burst if you, I don't know, if you don't take care of that in an appropriate way. So there's a lot of things to consider, and it can be summed up in a very simple short sentence, and that is, essentially everything changes with temperature, right? There's just no way around it. But so what do you do out of that now, right? As an optical designer, if you are developing an instrument and maybe there's no correct lens within the market already off the shelf that you can buy and use, then of course there's multiple suppliers you can call, including Kova, including Edmund, including probably also Schneider and many others. And you can just call these guys and say, all right, I need this, but I have a temperature spec. And then very often I personally get to see a temperature spec like operating temperature, say -10 to 60 or even smaller, 5 to 40. And every time there's a sentence below that that says optical performance is not supposed to change. And this is really just, physically not possible. It will change. The question is, how much are we allowed to change it? So, metrology has advanced to a level where you can really measure it. So this needs to be quantified, and this is where all the fun and the exciting work starts. It is quite an interesting challenge then also for the optical designer. It's actually a lot of fun to do that, to design a lens in a way that all the different movements you see happening in your lens, if you try to compensate all with each other. It's not different from designing a normal lens. Every single element in a lens design adds a certain amount of imaging errors, aberrations. And then the art of optical design is really just the art of combining multiple elements together so that the overall system imaging performance of the lens adds up nicely. So the bad lens over here is compensated with that lens, and then this part over here is compensated by another thing. And the same mechanism applies to an athermal lens. So if some index of refraction of your first element goes up, then you need to choose maybe the second, third, fourth element in a way that this change in the refractive index is compensated. So that's fun to do, but it takes time. So if you go down that route in a project, then you need to expect a significantly longer design cycle. It's an iterative process. You need to do a tolerancing afterwards to see if the performance is not only happening on paper or in Zemax, in the optical design software. You, of course, also care about, does it work in real life? And that's quite a detailed analysis that requires a lot of work and expertise. Also, because you're limited now all of a sudden with your material, it might be you need to make some part of aluminum. It might be you need to make the other part of steel so that the interaction of the entire system and temperature changes compensates each other and guarantees a stable level of quality. So all of a sudden you're limited in your number of materials. So maybe you have to choose a couple of elements that are higher cost. Definitely an option that's out there. And last but not least, depending on what you want to do and what you want to see this lens do, you might actually have to go down a route where you even have to develop custom metrology equipment. Especially things like beam pointing over temperature or MTF over temperature. This is not very commonly used, in my personal opinion, at least. I think there's a TriOptics machine that you can buy that does that, at least MTF versus temperature by now. I think a lot of that is actually coming from the recent trend over the last years that the automotive guys have such a big interest, autonomous driving and things like that. I think there was a big push on the metrology side where people said, all right, how did you guys in the optics industry measure that until now? And then our answer was, we take the lens, we measure MTF, we put it in a cabinet, we change temperature, we run some cycles, and then we measure MTF again afterwards. But measuring all of these parameters in situ, which is, again, eventually what matters to you in your applications, that has not been around for a long time, I think. So it's definitely worth to bring that topic up very earlier if you have a custom imaging lens project. And even for standard product. For standard product, you probably won't find this information at all, because I think I hope I made it transparent that this is a lot of work to analyze all of this. So for standard lenses, it's really, chances are very low that you find that in a data sheet. And so for standard lenses, there's of course the quick solution. You can just test it immediately. One last note, because I come to the end here. At the very end, of course, you don't care about the optic by itself, you care about the entire system, right? So that is what makes such an athermal lens design project so interesting. Yeah? You really need to exchange a lot of data on a very detailed level. So usually it takes one meeting a week at least for many, many weeks or months to get all of that correctly aligned throughout the design process, including the metrology. So yeah, a couple of questions I listed them here for you. You know, how's the lenses? How does the sensor inside your camera move with respect to the optics, if you use a camera at all? If you have just the sensor and do all the surrounding mechanics yourself, then the same question still applies, of course. How exactly is the optic mounted in that case? What material is the lens mount made of? What's his or its coefficient of thermal expansion, and so on and so on. So lots of fun and detailed technical discussions are going on there. And not only on the very detailed technical stuff, but also the entire application is something that you need to look at to really understand what's going on there. Are there fast temperature changes? Is there a directionality? So is all the heat coming out of one direction, or is it isotrope, if that translates to English? So a lot of fun discussions to have. And we really enjoy doing that here at Edmund. But yeah, in the very end, for standard parts, as I said, you can do, there's probably not a lot of value to do the analysis, because you can just take it and put it in on your test bed. So it's really just try and error on that page, on that state already. And if you're going on a custom project, then we can certainly talk you through about all the different options that are out there, at least here at Edmund, in terms of analysis, because there's a lot of things that can be done. And it really is getting a lot of attention within Edmund, this entire harsh environment topic, environmental specifications. So this is my last slide. We're going away from the technical content of the presentation a little bit, and just this very quick slide on kind of a company update, if you wish. Just a few weeks ago, this year, we actually opened a new design center. We already had one in Tucson, but now we got a new building, an additional building, not a new one. The old one is still there and fully loaded. So yeah, this is this particular facility is really just was built with the goal to support this kind of projects. So stray light analysis, vibration and shock, temperature, humidity, in terms of design, in terms of metrology, but also our project managers are sitting there. And we also have prototype production. This is a picture of the grand opening. Just in case you didn't know, Edmund is actually a family company. So this is Robert Edmund, the son of the founder, and here's Mari Edmund, his daughter. So they're still with the company. Just as a little small fun fact at the end. So with that, I guess I can conclude my presentation, and I'm happy to take any questions you might have, either now or at the very end in the big group discussion. Peter,
Thanks,
are you back?
Boris. I'm back.
Very good. Good to have you.
First time. But I see you make everything perfect, so I don't be needed, it seems.
Yeah, you gave me the opportunity to practice this in the last tech talks, so I felt comfortable. But I'm still happy you're back now.
So sorry, I had some technical problems, but now I'm back, and now it's the time for questions. And first question is, can floating elements designs be ruggedized?
Well, that's actually a very good question. I think maybe Daniel can also comment on that, because my personal experience is actually no. As Daniel already showed this picture, you want to move the optics around inside the barrel. So for example, this would be a ruggedized lens that is quite dumb in that way. You just move the entire thing back and forth and back and forth. With floating elements, and this is easy to ruggedize because you just drill a few holes in it and put glue in it, and then that's essentially it. With a floating element design, the optomechanics is really complicated. And from what I've seen, we only have a couple of floating element designs here at Advent. And when we try to put it on highly sensitive applications like 3D stereo cameras, and those are put on robots, we struggle to achieve the final results that our customer was looking for. So we remove the floating feature. We live with the restrictions in working distance range. Then we ruggedize it, and then it's no problem. But the floating feature gets lost in the ruggedization process. But I'm happy to also to hear Daniel's comments on that, since he also touched on that in his presentation.
Mm-hmm.
Well, I agree to you. I couldn't have explained it better. It cannot be ruggedized. So.
Thank you. Yeah.
Two companies, one opinion. Do you ruggedize lenses for underwater deep sea uses?
Oh, isn't that an interesting topic? I have to check with our new series that I mentioned at the beginning. You can put them a couple of meters underwater. I don't have the spec at the top of my head, but deep sea implies a lot of meters, and so I want to say no. So we don't have experience in that. We don't have a standard product yet. If you need a bunch of them, we can we can make a custom project maybe. But right off the shelf, we don't have anything for you here. Sorry.
There's a wish that the representatives display their contact details. Maybe you can write them in the chat so everyone is able to send you an email. I think that's also for Opto Engineering and COVA. And there's the last question before we start with the next presentation. Can a liquid adjustable lens like the one from Optitune compensate for the result of temperature influence?
Yes, they can. But please bear in mind, I'm laughing because the liquid lens itself is much more prone to temperature changes than normal glass. But you can do it, yes. If you have an application where you have changing temperatures, but you have enough time for an autofocus algorithm to run, then this is not a problem, yeah. Okay. Would be my short answer. And by the way, you can also find me on LinkedIn, of course. So if you want to reach out, I put my details in the chat here. But yeah, you'll find me if you, I hope at least.
Okay, Boris. I think we skip now to our last presentation for today. But Boris will be there after the last presentation for our final Q&A session. And Francesco, now it's your time.
Yes, of course. Let me just try to share my screen now.
Yeah, it's starting.
Is it working?
At the moment, I can see also the next slides.
Okay, hopefully now it's fine.
Now it's perfect.
That's great. Thank
Francesco,
you.
Please start.
Thank you. So thank you, Peter, for the introduction. I am Francesco Mondadori. I am product manager at Opto Engineering. And in today's presentation, I would like to talk about let's say a completely different subject with respect to the previous ones, and particularly I will deal with advantages of special lenses for top and side inspection over multi-camera systems. So in case you're not familiar with us, Opto Engineering is a world leader company based in Italy in telecentric technology, and with nearly 2 decades in the world of machine vision. We design, manufacture, and market a wide range of imaging components. In fact, over the years, we started from optics and telecentric lenses in particular, but then we expanded our offer, and today we can provide all the components, all kinds of components for machine vision, including different types of optics, like fixed focal length lenses, but also specialty lenses that we will discuss in the presentation today, advanced LED illuminators and pattern projectors, as well as industrial cameras, both area scan and line scan, imaging software as well, and last but not least, a complete range of accessories dedicated to all of the above. But now, after this brief, let's say, company presentation, let's come to the nitty-gritty of this presentation. So, depending on the specific case, certain types of applications such as OCR, OCV, barcode reading, but more in general, let's say defect detection, may require one or more of the following, which is top-down inspection, bottom inspection, a check of the inner walls, or a check of the outer surface of the samples. And anyone who's ever dealt with it knows very well that there are complications arising typically from a random orientation of the samples or some, specific features of interest, as well as a random positioning of the defects. So you don't know a priori where the defects will be. All of this is combined with possible space constraints, and in general, a top-down view like the one that is shown in the picture on the right is preferred. And typically, there are requirements of high throughputs in order to maximize the productivity. This is especially true for inline applications, of course. So to meet all of these needs, Opt Engineering designed a family of optics, the so-called 360-degree view lenses, that aim for an all-round sample control. These optics can be divided into three main types. We have outer inspection lenses, providing top and side view of the sample. We have inner inspection lenses, providing a bottom and or side view, depending on the design, as we will see. And then we have finally multi-mirror lenses, providing multiple views of the objects thanks to the use of mirrors, as the name suggests. So the first type of outer inspection lenses are, for example, those belonging to our PC series, which is based on a pericentric design. Pericentric means that the lens accepts rays that are diverging. So therefore providing a top and side view of the object as shown here in this picture. For these lenses, with these lenses, you can check diameters ranging from 7.5 to 60 millimeters with a maximum angle of view of around 24 degrees. Then we have another kind of outer inspection lenses, which is represented by our PCCD series. Let's say that the idea behind these lenses is very similar to the previous one. But in this case, we exploited a catadioptric design, meaning that we use mirrors to produce the image. So in this case, you will still have, let's say, you can still image the top and lateral side of the object, but at a different angle with respect to the previous case. The possible diameters range from 7.5 to 35 millimeters, so slightly smaller diameters with these optics. And as I mentioned, the angle is slightly different because, of course, depending on the model, you have a maximum angle that can range from 18 to 35 degrees. Then we have the other group, which is inner inspection lenses. And the first type is represented by our PCHI series that features whole inspection lenses. So they are based on a peculiar design that produces a concave field of view, so a curved field of view, allowing to view the lower, so the bottom and sides, inner sides of the cavities in this case. Cavities that can range from 10 to 120 millimeters, more or less, with an angle of view of 82 degrees. An interesting development we've been working on with these lenses is the integration of liquid lens technology. You mentioned, you already mentioned it before. So like the one with of Optotune lenses. And this allows for autofocus of samples to improve, of course, the ease of use of these optics. Then we have another type of inner inspection lenses, which is our PCBP series that includes borescopic probes. So you can see in this scheme that you have basically a cone, a viewing cone around the lens that enters inside the cavity to image the inner sides, basically. Diameters, the diameters of the cavities, of course, can range from basically 5.5 to 100 millimeters. And the angle of view is 60 degrees in this case. An interesting feature of these lenses is that they have an integrated illumination so that it's easier to integrate them inside the vision system. You don't need an external dedicated lighting system. Then we have the last group, which is multi-mirror lenses. And the first one is represented by our TCK series, where you have the integration of a telecentric lens with 4 mirrors. With these optics, you can check objects that range from 8 times 32 to 16 times 68 millimeters, depending on the model, with an angle of view of 90 degrees, because of course you have 4 mirrors, so for an all-round inspection at 90 degrees. The main advantage, one of the main advantages, let's say, of this series is that it provides a telecentric view. So thanks to it, you can perform precise measurements on the images. And you have an integrated top and back illumination that can be controlled independently, so that you can select which one of them you want to use, or either the 2 of them together, to improve, let's say, to optimize the acquisition. Then you have another type of multi-mirror lens, which is represented by our PCPW series, where you have the integration of a fixed focal lens and 6 mirrors, with the scheme that is reported here. And here you see the result of the, let's say, of an acquisition with this lens. So you have a top and 6 lateral views of the same sample. The diameters of the objects can range from 30 to 50 millimeters at an angle, viewing angle of 45 degrees. And finally, we have the last kind of multi-mirror lenses, which is PCMP series, where basically the principle is similar to the one we just saw, but in this case there is the integration of a telecentric lens with 8 mirrors. So you have let's say, a top-down view with a telecentric lens plus 8 lateral views with the mirrors. These lenses are meant for smaller objects, so ranging from 2.5 to 10 millimeters in diameter and at an angle of view of 37 degrees. Like our TCKH series, these optics benefit from a telecentric view, which is extremely useful if you want to do measurement, especially in the top-down view, in the central part of the image, of course. And another important thing is that they have an integrated illumination, so the integration is way easier. You don't need an external lighting system also in this case. But now let's go back after this brief excursus on the gamma. Let's go back to the initial problem, which is how to deal with applications where you don't know basically the position of the defect or the feature of interest a priori. A first possible solution, as reported here, is a multi-camera system, which has the main advantage that can provide a good resolution at 360 degrees. But on the other hand, it's typically characterized by a large footprint. You typically have depth of field issues, particularly with small and non-flat objects, because you're using high magnification lenses. Of course, you can always increase the F number. It means closing down the optics to increase the depth of field, but you will face other problems related to the lower amount of incoming light, and all the related drawbacks. And then you need a special hardware and software to reach high speeds, like the ones you can see here, like multiple bus ports, GPUs, and so on. The setup is very time consuming because you need to calibrate and perfectly synchronize everything in the system. And last but not least, greater complexity equal greater risk of components failure. So most of the times the simplest solution is the best in this case. Another possible approach is the line scan ones, which has the main advantage of providing very high resolution images, particularly efficient with elongated objects. On the other hand, the object must stay still during the acquisition because you need to rotate it. So it's not very compatible with inline applications. And you may have, again, depth of field issues with non-flat objects because you're typically using high magnifications. Plus, you need an additional area scan camera if you want to perform also a top-down or bottom inspection. And you need, again, special hardware and software like frame grabbers and so on. So because of all of these, aspects we just discussed, Optengineering designed its series of 360-degree view optics that provide a compact solution because you have just one camera, so you can acquire, you can perform an all-round inspection with just one camera, and typically with a top-down view, which is the preferred one, as we already saw. It's suitable for the inspection of medium to small samples, and it's compatible with inline applications. That makes it a preferred solution. You also have the advantage of using just a single camera, so the setup times shorten a lot, and then you have fewer and simple hardware components because you don't need something like frame grabbers that we just mentioned, or bus ports and so on. Plus, other important aspects are that you have you have the possibility to benefit from a dedicated illumination because we have a complete range of compatible ring lights, or in some optics, you also have the illumination which is already integrated in the optics. The lenses are also customizable in terms of resolution, so you have higher resolutions that are possible, dimensions, angle of view, illumination, and so on. And moreover, we also have a dedicated software library for unwrapping, which is this 360 lip suite. Unwrapping means that with these optics, you obtain a circular image of the sample. Thanks to this unwrapping feature, you can transform this circular image into a linear one, making it way easier to process after the acquisition. In this slide, you can see a comparison between the three approaches we just discussed, so multi-camera, line scan, and 360-degree optics. And you know, as you can see, 360 degrees optics offers several advantages compared to other solutions, mainly in terms of simplicity, both from our hardware and a software point of view, in terms of efficiency, and in terms of overall compactness of the system. This is what makes them an ideal solution for many real-life applications that we will see in the last part of the presentation that we're gonna enter now. So here we reported some application examples where you can see these special optics in action. First one involves pericentric lenses for the external inspection, so the outside inspection of vials. And more specifically, the purpose is to perform an OCR and reading the matrix code basically on the caps, the expiration date in particular here. The pericentric design allows to check the top and lateral sides, as we saw before. And as you can see here, thanks to this approach, it is possible to perfectly detect and read the expiration date without knowing a priori the bottle orientation, basically, which is a major advantage.
Francesco, 2 minutes left.
Yes, of course. Thank you. Then we have another application case where a pericentric lens has been employed to check the correct sealing of vials. So the so-called flip of caps. Possible defects include the absence of the stopper, the defective crimps, dents, the deformation of the flip off, or also wrong coloration, or scratches and deformations in general on the cap. So here you can see our pericentric lens in action. Then we have another example with hole inspection lenses to check the presence of residuals and contaminants in glass vials. Here you can see also a scheme of the concave field of view produced by these lenses that I mentioned you before. And as you can see, it is easy to identify the defects using such lenses for glass vials in this case. We have also another example with the other kind of hole inspection lenses, so the borescopic probe, that here are used to check the inner sides of a rotor. A rotor is one of the main components of electric engines, basically. And as you can see here, thanks to the borescopic probe, it is possible to check the presence, absence of any kind of feature here, or also deformations, inclusions, and so on. And here you can see the unwrapped image, the unwrapping feature I mentioned you before. Then we have also another application case with the smaller version of the borescopic probe, that we recently designed and we recently launched, which is this one here. Basically, the working principle is the same, it's just smaller with a more, which is suitable for smaller diameters. And again, you can look for blemishes, dents, threads, presence, absence here, because in this case you have small mechanical bores to be inspected, scratches, and so on. Then we have the last two examples with multi-mirror lenses. In this case, a TC cage, so the one with a telecentric lens and 4 mirrors, which has been employed to check for defects in cannulas, which are these basically these needles employed in the medical industry. And the lenses have been employed to check for the angle, bow, and degree of alignment. And finally, the last one is the inspection of the same sample, but in this case with different lens, because the focus was only on the tip of the cannula. So we wanted just to focus on the tip of the needle here. Yeah, then there is the last one, which is basically similar to the one we saw before, using a different kind of lens, but again on flip of caps here. So for looking for cuts, scratches, contaminations, and spots again. Okay, so thank you very much for your attention, and it's Q&A time.
Yes, now it's time for your questions. And if you have now any questions, please write. Is it a question for COVA, Edmund Optics, or for Opto Engineering? But we have 2 questions for Opto. What are the typical products that can't or can't be inspected with the TC cage lenses? Are there, for instance, materials that are particularly hard to illuminate with the integrated lighting system?
Well, we actually had a quite broad range of inspecting samples, ranging from fasteners. So they have been used a lot in the fasteners industry, because typically a rotating glass table is placed under the lens, and so the basically screws or bolts or nuts, whatever, are passes inside the lens, rotating, and so they can be inspected. Another interesting feature is that basically the TC cage has a hole on the top where the sample passes, and in that hole you can also add a macro lens. So also you can also have a top-down inspection of the same sample. So we also used it for also vials as well, as even if we didn't show it here, but it's also possible. Finally, just to mention, another particular application case is that because, as I mentioned, there is a hole on the top of the the part of the cage where the sample passes by, so in between the mirrors. In some cases, they are also used to inspect cables, because the cables are passed, let's say, inside the top hole, and it is possible to inspect the cable as it passes through the hole, passing in front of the lens and inside the mirror.
Mm-hmm. Oh, there are a lot of more questions. Can you just tell us camera manufacturers using your 360 degrees lenses?
Yeah, well, we had a lot of cooperations also with camera manufacturers. Just to mention some, we also cooperated with, for example, Cognex and Keyence as well, for some kinds of, specific systems that they are working on. Because, of course, as you can see, these are not standard lenses. So it's quite a unique offer that we can provide. So we have a lot of cooperation also with these ones as well.
And how far can the Perry optics to be mounted from the product?
Sorry, I didn't get the first part of the question.
Perry optics. PER.
Okay. Yeah, sorry. Well, the working distance, of course, depends on the model because resolutions, we have different models with different resolutions and fields of view. In general, they have a working distance range which is more or less the same with respect to telecentric lenses with the same size, more or less. So again, I can be more specific, but it depends. I could be more specific, but it depends a lot on the specific model you're interested in.
Mm-hmm. Boris, Daniel, there are also questions for you. Maybe you can go also online. And Francesco, there is maybe you could write your contact data at the chat.
Yeah,
so your email address, so people are able.
Yes, I just realized that before I wrote it down, but I sent it only to Boris because I was replying.
It's also good.
Sorry, Boris, but
no problem.
At least you have my contact now.
I didn't notice. Sorry, I would have let you know if I noticed that.
Boris, you mentioned temperature effects. Is there a standard equipment available on the market to measure these temperature effects on image quality?
There's this instrument from TriOptics I'm aware of that has been around for a year or two. I'm not sure about that, but so there's some instruments. But yeah, as I said earlier in my presentation, it really depends what metric do you want to look at, and at what level of accuracy do you want to really measure it? Because we're really talking about very, very fine details very, very quickly because of all that subpixel interpolation thing. Yeah.
Mm-hmm. Daniel, can you also modify existing lenses to meet customized mount requirements?
Well, this also depends. It depends on the backfocal length and the mechanical requirements. If it fits technically, yes, it can be done. But in some cases, it's a completely new optical design.
There's a question. I think we had it, but there was a crash from my PC, so I repeat it for you, Daniel. What about half-inch sphere lenses? Any plans for it?
I think we answered this question already. I said we can cover with the 1 inch, we can cover the half-inch, but specifically for the small sensor size, there is no plan to develop it.
Mm-hmm. And for Francesco Opto, there's a question. Do you provide any telecentric lens on image side only?
On image side only, yes, we do have also not only bi-telecentric lenses, but some of them are only telecentric, let's say, image sides.
Mm-hmm. And there's a question about the resolution of your optics. Which camera resolutions are these optics designed for?
Yeah, well, as I mentioned before, there are different models for different resolutions, but in principle, I will go a little bit more into the details afterwards, but just a short, introduction. The problem with resolution is that the higher the resolution, the lower the acquisition speed, typically, given that all the other, parameters are the same. So, as we mentioned before, one of the main advantages of these optics, these 360 degrees optics, is that they are meant to be used mainly for inline applications. And so they should be as fast as possible. Nevertheless, we developed also other models for high resolutions because initially they were developed only for 1/2 of an inch sensors and 2/3 of an inch sensors. But recently we also launched higher resolution versions for 1 inch sensors, 1.1 inch sensors, and 4/3 of an inch sensors, depending on the series. Not for all the series, but for some series, it was possible to do it. Yes.
Mm-hmm. Boris, your presentation seemed to be focused on fixed focal length lenses. Is it different for telecentric lenses?
No, it's not. I was really just showing pictures from fixed focal length lenses, but the same fundamental principles apply also to telecentric lenses. I think that goes for shock, vibration, and also temperature. Maybe one detail on the telecentrics: if they are image space telecentric, then they might be able to deal a little bit better with the beam pointing issues that you see from fixed focal length lenses. Because if the chief ray angle is 0 degrees and things get shaky a little bit, then you get just more, how do you say? You have more freedom to mess things up a little bit if the image space lens is tetracentric.
Daniel, how long does it take to develop a new lens from the scratch? Are we talking about weeks, days, months, years?
Usually months, so it depends, of course, also on the complexity of the design. But after the design has been fixed, it would take roughly 3 months to deliver the first samples.
Thanks. Francesco, does multi-mirror maintain advantages of telecentric lens? We can't hear you. You're mute.
Sorry.
No
My
problem.
bad. My bad. Yes. Multi-mirror lenses maintain the same advantages of telecentric lenses. Of course, whenever you add optical elements, you need to be careful because you can add also imperfections of some kind, So provided that the mirrors are good quality ones, which is the desirable thing in general, it's not a problem, and you can maintain all the advantages of telecentric lenses also when combined with mirrors. Definitely.
I'm looking, are there any more questions? There's a question once again to Francesco. Are there any new developments for 360 degrees lenses you're currently working on, maybe which we'll see in the near future?
Yes. Spoiler alert.
Trust me, I'm an editor.
Yeah. Okay. Well, yeah. We've been working a lot with liquid lenses technology because we find it extremely interesting for many points of view. And so we are working on the integration of liquid lenses also on other models of 360 degrees lenses. For now, we only integrated them in our PCHI, so the old inspection lens I showed you before, but also we are working on integrating them on other models. Again, as I mentioned before, we are also working on, in general, higher resolution versions of other optics, because it's true that there are all the problems related to the acquisition speed that I mentioned before. But on the other hand, we see that in the last years, the trend is moving towards higher resolutions in general, both for telecentric lenses, entocentric ones, and I think my colleagues Daniel and Boris can confirm it. With respect to a few years ago, let's say the use of higher resolution lenses is becoming more and more diffused. So also for these specialties, we are working on higher resolution versions as well.
Mm-hmm. So I think now it's the last chance for your questions. As always, I'm counting to 5. Otherwise, we are coming to the bitter end. Maybe it works, we see, and it works. There's a question about what is the loss of resolution using sphere wavelengths. So I think, Daniel, it's a question more for you.
What is the loss? Well, this lens optical design I just showed has the optical design adapted to a resolution in short-wave infrared. So generally speaking, now the existing short-wave infrared cameras don't really have a high resolution. Maybe that is the question is referring to that one. So the existing short-wave infrared cameras really have quite a low resolution with pixel size around 10 micrometer. But the one I pointed out, the Sony sensor has a much higher resolution, in fact.
I hope this question is answered. Otherwise, now it's a chance to ask another question. And does your SWIA lenses also work with Basler cameras, I think?
With Basler?
With Basler, yeah. I think, does your optics work together with a Basler camera?
Well, it depends what transmission the sensor have. I think, well, I think they have some cameras which go very far into near infrared. For that case, if you need to use this part of the sensor which goes very up to near infrared, then it is a good choice. Otherwise, I think they don't really have cameras going up to shortwave infrared. So yeah, so if you just work in this very near infrared part, then sometimes it might make sense to use the shortwave infrared lens.
Mm-hmm. Now it's the time. The experts are here. It's the time for your questions, and otherwise I will really start to count. And now I start to count. 1, 2, 3, 4, and it's 5. And I think we are at the end of our webinar. So thank you, Francesco, Daniel, and Boris, for your presentations. Thank you to all the listeners and viewers. You all will receive a link with a recorded webinar until tomorrow. Hope to see you soon again, maybe next week, where we have another webinar. And I think there's a final question arising now. And I think it's for everyone, for you, the future of C-mount. Any last words from Boris, Daniel, or Francesco?
For the time being, we'll stick with it.
Yeah, I think so.
The quite established standard, so I don't see it changing.
That's perfect. Finish and end. So thanks all. And now, bye. See you soon. Stay healthy. Bye.
Stay safe.
Bye,
Thank
everyone.
you.
Thank you.
Thank you.